Hi everyone. Let me start with a fun thought. When you lift a heavy bucket of water, you feel your muscles ache, right? But once the bucket is sitting on the shelf, it looks completely innocent, just standing still. So, where did all your hard work go? That effort is stored as potential energy, energy due to position in a gravitational field. Gravity, being a conservative force, guarantees that the work done only depends on start and end positions, not on the path. Near Earth's surface, the force is almost constant, F equals mg. If you move the bucket from height h1 to h2, the work done is mg multiplied by open bracket h2 minus h1 close bracket. That's why we often write potential energy near the surface as U equals mg h, simple but powerful. Now let's extend the idea. What if we move far away from Earth, where gravity is not constant? Think of a satellite orbiting thousands of kilometers above. At a distance r from Earth's center, the gravitational force is F of r equals gm em divided by r squared. To find work in moving from R1 to R2, we integrate. Work equals negative integral of gm em over r squared dr from R1 to R2. Solving, we get minus gm em times open bracket 1 over R2 minus 1 over R1 close bracket. This leads us naturally to a potential energy function U of r equals minus gm em over r plus some constant. And that constant depends on our choice of 0. So unlike the simple mgh near the surface, at large distances potential energy follows a 1 over r law. So, where is this 0? By convention, we set u equals 0 at infinity, meaning if two objects are infinitely far apart, they don't influence each other. That makes gravitational potential energy at distance r equal to U equals minus gm em divided by r. Notice the minus sign. It tells us Earth and the object form a bound system. To free the object completely, to escape, we must supply energy. In fact, this negative potential is the reason planets don't just drift off into space. They are trapped in this invisible gravitational well. Now imagine two particles, mass m1 and mass m2, separated by distance r. Their potential energy is U equals minus gm1m to divided by r. As they move closer, the energy gets more negative, meaning you'd need to put in work to separate them. For larger systems, like star clusters or even molecules, the total potential energy is found by adding up the energy of every unique pair. It's like counting every handshake in a big room, and it quickly adds up. Let's solve a classic NCERT-style example. Suppose 4 equal masses are placed at the corners of a square of side length L. To find the total potential energy, we add up contributions. There are 4 sides, each pair at distance L. Then there are 2 diagonals, each pair separated by root 2L. Adding these, we get U equals minus gm squared over L multiplied by open bracket 4 plus root 2 close bracket. This is a neat demonstration that system potential energy is just the sum over pairs, no shortcuts, no magic, just physics bookkeeping. Now let's link this to real life. Every time you lift an object, you're increasing its gravitational potential energy. Drop it, and that energy converts to kinetic energy. In space, changing a satellite's orbit means changing its potential energy. Rockets burn fuel not only to go faster, but also to climb out of Earth's potential well. On the cosmic scale, the fact that gravitational potential energy is negative explains why galaxies and stars remain bound together. If it were positive, the universe would have flung itself apart long ago. So whether it's your falling pencil or a rocket escaping Earth, gravitational potential energy is silently shaping the story. Let's tie everything together. Gravitational potential energy is the stored energy due to the position of masses in a gravitational field. For a mass near Earth's surface, U equals mgh. For general distances, U equals minus gm over r. And for two masses, U equals minus gm1m2 over r. It is always negative for bound systems, which is why planets, satellites, and galaxies remain connected by gravity. This concept forms the backbone for topics like orbital mechanics, escape velocity, and astrophysics. So next time you struggle to lift your backpack, just smile. You're not just fighting weight, you're building gravitational potential energy, the same principle that controls satellites and stars. See you in the next session where we'll continue unraveling the wonders of physics.